In the previous sessions, we understood what happens when we apply an AC waveform to a resistor or an AC waveform to an inductor. What happens when we apply AC voltage or an AC waveform to a capacitor? Right, so an AC waveform is by definition changing with time. If we connect a capacitor to a constant voltage source like a battery or DC source, the capacitor will charge very quickly to the same voltage as the source. So a capacitor will try to maintain the same voltage across its terminals as the source. This works both ways. If the source voltage goes down, the capacitor will discharge. It will lose charge and come down to the same level. And if the source voltage increases, the capacitor will charge up. It will accept charge and come up to the same voltage as the source. So the capacitor voltage is very closely following the voltage of the source. So in this case, let's see what happens when we apply an AC voltage to a capacitor. So here we have a simple circuit. Containing a capacitor, and this capacitor is connected to an AC source. So this is our AC source. It is giving you an AC voltage waveform. Now the voltage across a capacitor at any given time, V, can be defined as V is equal to Q upon C. Now Q here is the charge on the capacitor plates and capital C is the capacitance of the capacitor. So we can say that Q is equal to V multiplied by C. As I said, a capacitor tries to follow the same voltage as the source. It will try to increase or decrease its voltage in response to any changes in the source. What about current? For a condition where the capacitor is connected to a direct current source, a constant voltage source, there is no current. Once the capacitor charges, it will neither accept any more charge and it will not give any more charge. The current is zero. But what happens in a time varying case? So we already know that the differentiation of charge with respect to time gives us current. So if we want to find out what is the current across a capacitor, let's use our definition. So I is equal to the differentiation of Q with respect to time, which is equal to the differentiation of Vc with respect to time. Now in this case, the capacitance is a constant, so we can't differentiate that, but the voltage is changing with time. So the voltage waveform for a circuit, an AC circuit, can be given as V is equal to Vm sine omega t. So what is Vm here? It is the peak voltage reached by the AC waveform. So we can write this equation for current as C d by dt Vm sine omega t. So if we differentiate this, Vm is a constant, we can write this as Vm c omega cos omega t. And this is the equation that gives us the instantaneous current across the plates of a capacitor at any given time. Now, if you were to write the current for a capacitor in the same way that we define the voltage for the capacitor or for an AC system, so current is equal to Im sine omega t plus pi by 2. Now, if we were to define the current in this system the same way we defined voltage, we would find that we can write I as being equal to Im cos omega t. If we compare these two equations, we see that we can write the current as I is equal to Vm times C times omega. This is the peak value of current reached by this circuit. So we can write Im in terms of the peak voltage as omega C times Vm. Can we rewrite this equation to be more informative to us? I can write this as omega C multiplied by Vm I can write this again as Vm divided by 1 upon omega c. Now, why am I trying to write it this way? If you look at a resistive circuit, so here we have a resistive circuit. We know that by Ohm's law, for a resistive circuit, the current is equal to V divided by R. In a capacitive circuit, we are noticing that the current at any given time is given as Vm upon 1 upon omega c. So in a capacitive circuit, 1 upon omega c is performing the same role as R performs in a resistive circuit. So 1 upon omega c is in a sense controlling the amount of current in a capacitive circuit, but R, that is the resistance, is controlling the current in a resistive circuit. So they are playing similar roles. So 1 upon omega c, this quantity, can be written as the capacitive reactance of this capacitor, or XC. So just as we say that current in a resistive circuit I is equal to V upon R, we can say that current in a capacitive circuit IM is equal to Vm upon XC, where XC is equal to 1 upon omega c. It is very important to remember that even though they are performing similar roles, now it is very important to remember that while capacitive reactance and resistance are performing very similar roles, they are not the same. The physical mechanisms behind them are very different, and we will see what crucial difference exists between them very shortly. So this gives us a view of what happens when you put an AC voltage to a capacitor. How can we understand this in the context of these signals, the waveforms of these signals? So here is where phasor analysis can help us. Let's see how. So here we have a unit circle. And here is the actual sinusoidal waveform. So this is a sinusoidal representation of the signal with respect to time, or omega t. And here is a representation of the same phenomena, but here the forward movement of the graph is turned into a rotation. So we are rotating around the graph. So if we take the voltage phasor, this is our voltage phasor, and it completes one complete rotation on this circle. That is equivalent to a complete cycle of this sinusoidal waveform, which means that every point on this circle corresponds to a unique point on this sinusoidal graph. What else does this tell us? So we can pick up any random point here. Let's pick up this. And this will correspond to, if we produce this, this point on the graph corresponds to a rotation of the voltage phasor. So the voltage phasor is rotating by omega t, which corresponds to this position on the sinusoidal graph. So the phasor is continuously rotating. We are observing the rotation at a point in time. So the voltage has reached a particular value. In this case, the height or the vertical component of this phasor will tell us the instantaneous value of voltage at that moment in time. So this will be equal to Vm sine omega t. What about current? We just understood that the waveform for current is for capacitor given as Im cosine omega t. Now there is an interesting little identity here. We know that cosine omega t can be also written as sine omega t plus pi by 2. In other words, the waveform for the current Im cos omega t can also be written as Im sin omega t plus pi by 2. So it is in a sense leading, it is ahead of the voltage waveform. The current is ahead of the voltage waveform by exactly 90 degrees. The magnitude of current will be less than voltage, of course, because the capacitive reactance will reduce the current below the value of voltage. So we can describe this current with a smaller unit circle. So here we have a smaller unit circle. And for that same instant of time at which the voltage is equal to Vm sin omega t, at that same instant of time, we will have a current, and the current will be represented by another phasor, which will be shorter and will be at 90 degrees to the voltage phasor. So here we have the amplitude of the current in this system, which is given by Im cos omega t or Im sin omega t plus pi by 2. So we understand that in a capacitive circuit, the current waveform is leading the voltage waveform. It will be ahead of the voltage waveform. It will look something like this.
Manorama Horizon. Learning made simple.